scattering amplitude is not allowed to have branch points at random locations in the kinematic domain. It can only have branch points at a location that corresponds to a possible intermediate particle exchange going on shell. Bose symmetry, right? So for example, for MHV amplitudes, once you, the residue of Bose symmetry at the level of color stripped amplitudes is cyclic symmetry, so I should really call this cyclic symmetry. For example, for MHV amplitudes, if you factor out the tree level Park-Taylor factor, then the resulting function should be completely dihedrally symmetric under exchange of the particle labels. And importantly, collinear limits place very strong constraints on scattering amplitudes, as well as near collinear limits, where there's been an enormous amount of recent progress using a complementary approach of operator product expansion for Wilson loops, primarily by Basso, Sever, and Vieira. They can provide data on the near collinear limit expansion of a variety of scattering amplitudes, which you can compare with your odds and try to extract the coefficients. So the idea is the Bootstrap program, it allows you to determine amplitudes without doing integrals, and even without needing to know the integrands. So ultimately, one of the long-term goals of this research program is to ask the question, does there exist a simple set of physical and mathematical criteria whose unique solution, or whose allowed solutions are exactly the family of scattering amplitudes that appear in supersymmetric Yang-Mills theory? So what we've seen today is that the functions that you get are not random functions. They have a very rich mathematical structure. Many of the simplest ones can be expressed as generalized polylogarithm functions, which are elements of the Hopf algebra. There appears to be some deep connection between the cluster structure on the kinematic domain, and then of course there are a number of important physical conditions on these functions. So these are certainly not random functions. In fact, Sasha Goncharov has told us several times that the way to think about this, I mean, he's so surprised that these functions even exist. It's almost inconceivable that the scattering amplitudes of super Yang-Mills theory even exist, given all of the demanding constraints on their structure. So maybe there's some sense in which this class of functions is mathematically unique. You know, is there a mathematical question to which these are the unique answers? So I'm out of time, and I could say a lot more, but I think I've utilized my time well. So thank you.
Any questions? Yes.
But even in any loop for super Yang-Mills, we know that at a certain level, at 10 points,
Good.
loops,
Thank you.
we might have to go beyond this.
We certainly will have to go beyond, right. So certainly it is not true that all, there's a Malmquist bias here, because the vast majority of results for finding integrals that you see in the literature are generalized polylogarithm type. And yet, we expect that amongst the set of all possible Feynman diagrams you could conceivably look at, the ones that are generalized polylogarithm type are like measure zero. But they're the ones that are easiest to analyze. Okay, there are famous examples starting at two loops. Sunset diagram with masses evaluates something involving an elliptic function, and we know that functions of this complexity class, as you alluded to, they start appearing even in the beautiful n=4 super Yang-Mills theory. Functions of a higher complexity class start appearing here. So definitely there will be some deeper mathematics that's required to understand these more complicated elliptic type functions or beyond. I just want to say one thing. I want to get it on the record here because I'm being videotaped, and this is a totally speculative comment, but it might be studied by Bloch, Van Hove, and Weinzierl. This diagram that evaluates to an elliptic interval, it can be written as an infinite linear combination of dialogues. Okay, with a series of arguments that take the form q to the n in some convention. Okay, so back here when I was talking about symbols, I didn't state this explicitly, but to be mathematically rigorous, you should always, when you're talking about generalized polylogarithm functions, you're interested in symbols that are finite linear combinations. Okay, so maybe it's the case that if you relax that and you allow formally infinite linear combinations, then you can treat, to some extent, these kinds of integrals as having symbols. And this connects with something else, a big elephant in the room, which is that the cluster algebra associated with confen of P3, as soon as you go to 8 points or higher, it has infinitely many cluster variables. So it would seem a shame if the mathematicians provide us with an infinite number of cluster variables, and yet Super-Yang-Mills theory doesn't make use of them. So maybe there's some sense in which this type of integral evaluates to an infinite linear combination of weight 4 polylogarithms that somehow involves the infinite number of cluster coordinates that are available in this cluster map. This is totally rampant speculation, but it's just intriguing that these two infinities start appearing in almost the same place.
I think one more question.
Go ahead.
I just wanted to make a short comment about that function because it ties the symbol of that box ties back to the Fox by Washing and Hyman, where they were looking at very similar functions, which is that first entry there isn't totally random. In fact, you can assemble it into x plus x minus, which is actually one of the original coordinates u,
Yeah.
and 1 minus x, 1 minus. Yeah, so that has something to do with these conditions of not having bad branch points.
Yeah. Yeah.
Wrong places.
Yeah, so just to amplify that comment a tiny little bit, what Lance is pointing out is that you can use the multiplicative property here to combine these two terms. Maybe I should have done that. You can rewrite this, at least that term, you can combine like that, so plus other. The first entry in any symbol tells you, so the zeros of the first entry of the symbol tell you where the branch points are. And I said, but didn't write any equations, that you can only have physical branch points. So in this example, you couldn't have had just x minus or just x plus or 1 minus x plus as a first entry of your symbol. It has to be this combination on physical grounds. And when we go through this program of implementing mathematical constraints and physical constraints, this is one of the most difficult but potentially most constraining aspects, is that the cluster structure and these physical branch cut constraints seem almost completely orthogonal to each other. So together they really nail down the amplitude to a considerable extent.
Let's thank the speaker one more time.